Greetings, and this is Homework Help with Jen, and we're looking at molecular complete ionic and net ionic equations. This is the second video in this series. Okay, so what we're going to do today is we're going to look at some special cases for this. Okay, now the first one that you'll see up here, we have sodium nitrate and potassium chloride. So we're going to start by following our rules again. Okay, and that first rule, step 1, find the ions on your ion list. And here I have sodium and nitrate and potassium, sorry, and chloride. Okay, so we have Na plus, NO3 minus, K plus, Cl minus. So that was our step 1. Step 2 is to combine our ions to create formulas. Okay, well, this one is actually easy because they are all one-to-one. So now we have NaNO3, and we're assuming them to be aqueous because that's what they're asking about, our precipitation reactions. Okay. Now if this were our molecular equation, and this would sort of be the beginning of our complete ionic equation. Now our step 3 is to place formulas on the reactant side of the molecular equation and ions on the reactant side of the complete ionic equation. And I sort of have done that a little bit by accident. And now what we're going to do, I guess I'll show the complete ionic as well. I won't skip any steps. All right. Okay, and that was my step 4. Now this is actually a special case. And the reason for that is with our next step. And it says to finish molecular equation indicating a precipitate. Okay. Oop, you know what? Sorry about that. This is the one I was looking for. Okay, and this says that step 4, look at the solubility rules to determine if the reaction will form a precipitate if the ions switch partners. Okay, now in this case, we take a look at this and we say, we know that sodium nitrate is aqueous and we know that potassium chloride is aqueous. So what happens if they switch partners? And we get potassium nitrate and sodium chloride. Well, if we come over here to our solubility rules chart, we see that our nitrates are soluble. Our alkali metal cations are soluble. And our anions, chloride, bromide, and iodide, are soluble, except with these cations. But we don't have one of those. That means by rule 1, 2, and 3, everything in here is soluble. If you get that special case, then all you need to do is write no reaction. And you're done. Now let's look at another special case here. And we have barium hydroxide and aluminum nitrate. And now the question is, well, why is this a special case? First of all, let's go ahead and finish our steps. Step 1, remember, is find the ions on your ion list. Okay, so I would say, okay, here is barium and hydroxide and aluminum. Where did I find? There we go. Aluminum and nitrate. Okay, so I found my ions, and I am going to combine them to create formulas. So first I had that barium and hydroxide and aluminum and nitrate. Now what I need to do is I need to combine them to create formulas. And this time I was prepared, so I set those up so that I could make the equations right in there. So now we have our molecular equation. So now I have Ba2 plus and OH minus, so this becomes BaOH2, and I'm going to list that as aqueous because that's what's understood when we're doing this. And then I have aluminum nitrate. And that's definitely going to be aqueous because of our nitrate. The next thing here was our step 3. Place formulas on reactant side of molecular equation and ions on reactant side of complete ionic equation. And I've sort of set that up. And I'm going to finish putting on my states. And I'm going to put in my yield signs. And a plus in here so that I'm all set up. Okay. Now, why is this a special case? Well, this is a special case because, and it's not really listed on this because this ion list lists insoluble, marginally soluble, and slightly soluble things all together. If we come down here to the anion hydroxide, we see that it tends to be insoluble. The notable exceptions for this are sodium hydroxide, potassium hydroxide, and ammonium hydroxide. However, barium hydroxide is slightly soluble, so that means that it will precipitate out, but in very low quantities we can get it to become aqueous. However, aluminum hydroxide is completely insoluble. Okay, so this is the part where we are looking at our solubility rules to determine if the reaction will form a precipitate if ions switch partners. Okay, and that information about slightly and marginally soluble is in your textbook and your slides. Okay, so we know that barium hydroxide is slightly soluble, which means a small amount of it will stay in solution. A large amount of it would precipitate out, but a small amount would go in solution, and that's why we have a small amount of aqueous barium hydroxide here. However, aluminum hydroxide is completely insoluble, which means that our aluminum hydroxide will be our precipitate. Okay. So now what I'm doing in here is I'm doing that step 5 to finish the molecular equation indicating our precipitate as solid. And so now to finish this, we take our barium and our nitrate and we include that here, BaNO3 2, and that will be aqueous. And there I finished my molecular equation. Now my step 6 was to finish the complete ionic equation, showing the precipitate as solid and all else as ions. So I will do what I have done here as well, and I'm going to leave my precipitate as a solid, AlOH3S plus, now I know that nitrates won't precipitate out, and I show that here as aqueous, so we will still have barium ions and nitrate ions in solution. Step 7 is to balance. Okay. So I start by taking a look at my molecular equation. I have BaOH2, AlNO3, AlOH3, and BaNO3, 2. Okay, so now I'm going to start by saying, okay, well I have a 2 on my hydroxides there, and I have a 3 on my hydroxide here. Okay, now I know that 2 times 3 is 6. So the way I'm going to balance my hydroxide is by putting a 2 here so that I have 2 times 3 or 6 hydroxides, and by putting a 3 here so that I have 3 times 2 or 6 hydroxides on this side as well. And now I notice that I have 3 barium ions here. So I'm going to come over here and see that I have barium nitrate. I need 3 bariums here as well. So I'm going to put in a 3 right there. And now I look at my product here. I have 2 aluminum hydroxides, which means I need 2 aluminums on my reactant side. So I have to place a 2 here. And now I'm going to check my spectator ions, and I see that I have I come over here and I see that I have 2 times 3 or 6 nitrates, and 3 times 2 gives me 6 nitrates. So now I can see that my molecular equation is balanced. So now comes this sort of tricky place where we're putting our coefficients into our complete ionic equation. And here I see I have 3 bariums within my barium hydroxide units. So I will put a 3 here in front of my bariums. And here I have 3 times 2 or 6 hydroxide units. And here I have 2 of my aluminums. And then I have 2 times 3 gives me 6 nitrates. Now I had 2 complete aluminum hydroxide units, so I will carry that through here as well. And here I have 3 of my barium nitrates, which means that I have 3 barium ions here, and 3 times 2 or 6 nitrate ions here. And that is the balancing for this one. My last step is always to write the net ionic equation to show the precipitate. And so what we are doing here is we are identifying our spectator ions and basically leaving them out of that last step. So here I have 3 barium ions, and here I have 3 barium ions. So I will go ahead and just circle those, because that is something that's not changing. That's a spectator ion. And here I have 6 nitrates and 6 nitrates. And those aren't changing. But here I see that my aluminum ions and my hydroxide ions are becoming aluminum hydroxide. And in this last step, where I identify the where I identify the net ionic equation is I'm just going to write these down. Now, I have a habit of always writing my cations first. It's not necessary. So 2 aluminum ions plus 6 hydroxide ions, and that's just right there, is going to yield this 2 aluminum hydroxide solid. And that would be the net ionic equation for that.